Hello, welcome to the University of Lincoln's Christmas lecture series from the College of Science. The lectures will take place over the next week, with 4 taking place online at 1 p.m. and 1 lecture in person tomorrow evening. There is a link in the chat to our website where you can find details of the talks, along with joining links and instructions. Now it is my pleasure to introduce Dr. Phil Sutton, who will be talking about how to grow a moon. Merry Christmas.
So welcome everyone to this Christmas lecture about moons. So what I wanted to do with this talk really was to talk about where moons really come from. How do you grow a moon? Because they're not all made in the same way. They have a variety of different mechanisms which can place a moon around a planet basically. But I think the first thing we kind of really need to start with is what an actual moon is. Actually, I probably should start with what my area is really. So I'm obviously a senior lecturer in astrophysics at Lincoln. My research areas are focused around planets, moons, rings like Saturn's rings, and anything like that really. I'm really focused on the planetary sort of side stuff. So this talk kind of relates to some of that area that I'm working in as well. So what is a moon? Well, the key thing about a moon actually is that it will orbit a planet. So I've got a diagram here. You've got the sun in the center, and you've got the Earth going around the sun. And then you've got other objects like minor planets, asteroids. They also go around the sun as well. But the thing that distinguishes a moon from something like an asteroid or a minor planet, or even a planet for that matter, is its orbit, and it is the orbit around the planet. So a moon will orbit a planet, and a planet then orbits a star. So that is one of the key defining features, really, of what a moon is. And a moon isn't defined necessarily by its size. So we may think when we think of a moon that moons are going to be fairly small, and because they're orbiting a planet basically, but that's not necessarily the case. So I've got some examples here. So we've got Ganymede, which is actually our largest moon in our solar system, that orbits Jupiter. You've got Titan, which is a moon that orbits Saturn, and it has a very significant atmosphere. Those are 2 very large moons. And then you have Mercury, which is actually a very small planet and is smaller than some of our moons. And then Pluto, which actually is not really a planet, it's a minor or dwarf planet. And those are kind of approximate sizes, really, of them. And you can see that some of these moons are quite large. So it's not the size of the object which gives us the definition of a moon, it's its orbit, how it's moving. It has to be on an orbit around a planet. So that's the key defining feature really. And what I want to have a look at as we go through is how do they get there? Because they're not all created equal. So you've probably got some here that you might recognize. The one right in the middle, that's our moon. You should be able to recognize that one. We see that most days if we have a nice clear sky, although that's not that common here. And you have the Galilean moons, which are the 4 large moons of Jupiter. Now, if you've got a small telescope, a pair of binoculars, you don't need anything quite very big to see these, but you can see those quite easily from Earth with very, very small telescopes. And they're quite good to have a look at. So those around Jupiter, you've got Triton around Neptune, and then you've got Rhea around Saturn. Now, all of those got to their current location and ended up moons of those planets through different reasons. So something happened to each of those that was slightly different that ended up them being a moon or creating them as a moon around that particular planet. We're going to have a look at those various different mechanisms. And this is just an overview of some of the main ones that can help form them. So I'm going to start with the Earth-Moon system. Reason being is we're probably familiar with the main theory which caused the Earth and the Moon as we know today. And we think that there was the early Earth and then Theia, which was a Mars-sized planet that then impacted us early on. And that then left a disk of debris around the Earth. So think of Saturn's rings. It would have been a little bit similar like that. But then that disk of debris then quickly coalesces to form our moon. And that's what we think might have happened to form the Earth Moon system, that we had this giant impact from a minor or dwarf planet, or even a planet size object actually. And then we end up with the Earth Moon, and there's a variety of different reasons why we believe that's the case. But the giant impact scenario is one mechanism that can put a moon in orbit around a planet. And I suppose you want a bit of an illustration, really, for what that might look like. It's a fairly destructive process, actually. And in fact, some recent research, this, I think was this year or the year before, or relatively recent, was that this process of this smaller planet hitting the Earth and forming the Moon was actually very, very fast. So in astronomical terms, things can take millions of years, and then we classify that as quite fast, actually. But on the case here, we believe the Moon must have formed actually in only a matter of hours after the original impact. It was a fairly violent impact. It would have completely mixed up, or mostly mixed up, the two bodies, and then we ended up with a new Earth, and then we had this new object, the Moon. And this has happened, we expect, probably from other planets as well. And one of the other examples I will show you will be Uranus. So if we go to the next one, similar sort of idea. So this time round, instead of it being like an artistic video showing you the collision, this is a simulation similar to kind of the work that I do, where I'm modeling a system, an astrophysical system. You've got a minor or dwarf planet hitting the early Uranus. Now, the collision was slightly different. It's thought that that's what might account for knocking it over 90 degrees, because Uranus's rotation is tilted over 90 degrees compared to ours, which is around about or just over 20 degrees. And Uranus has rings. So on the left-hand side there, you can see some of its rings, and the moon's then within those rings. And a lot of those are then thought to have formed probably from that encounter or that impact earlier on. Now, most of the outer planets also have rings as well. So it's not just Saturn. Jupiter, Neptune, and Uranus all have ring systems as well. Actually, there are some asteroids with rings as well, but that's a different story. So it's not just Earth that's had a giant impact, and it's thought to be a relatively common occurrence. These things happen early on when the planets are still forming. But that's not necessarily the most common way that a moon might end up in orbit around a planet. In fact, we expect them to form with the planets themselves. So here we've got a kind of gas giant forming in a gaseous disk. This disk is orbiting a star or the early sun. So in the center, you would have this young sun that is still forming. So all that gas and dust is still falling onto the star and it's still growing. It's not a fully formed star yet. But whilst that's happening, material in that disk starts to coalesce, and the gravitational forces bring it together, and you get planets forming in that disk. And that's how we think planets form. But during that process as well, the planets almost have a disk around them, and on a smaller scale, you get planet or moons forming around the planet. So they kind of form together with the planets as they all form together around the young sun or star. And an example of that is actually Jupiter's Galilean moons. So Io, Europa, Ganymede, Callisto are thought to have formed with Jupiter in this early gaseous disk that was orbiting the planet whilst it was still forming. So as that material is still falling onto the planet, it can coalesce and create these moons here. And a good example is to kind of not necessarily back it up, but show one of the consequences of that is looking at this video from the Juno spacecraft. So the Juno spacecraft was around Jupiter, and as it approached Jupiter, you've got this really nice video. You can see Jupiter rotating anti-clockwise, and you can see the Galilean moons orbiting anti-clockwise as well. Now, if the moons formed with the planet, you'll find that they orbit in exactly the same direction that the planet rotates. So basically, conservation of certain laws means that they're going to be rotating the same direction. It takes a lot of additional energy to change rotations of things and make moons go the opposite way. So when they form together, they collapse from that same cloud. They're going to have the same direction. So Galilean moon is a good example of that, really. Now, the next one is from a tidally destroyed moon. So here we have Saturn's rings. So Saturn's rings, they're more significant than the other ones. So Jupiter, Uranus, Neptune, they all have rings, but they're not very large or massive. We struggle to see them from Earth. But Saturn, you can again see those with a really small telescope. And we think that those rings were formed from a tidally destroyed moon. So what's happened here is a moon has got too close to the actual planet. And when it gets close enough, its own internal gravity can't hold itself together. And actually, the tides from the planet tear it apart. And we think that's what might have formed the ring system of Saturn. And if you think about how the moon or the moon actually causes tides on the Earth, it causes a bit of a bulge in our oceans. And it's the same idea here. If you have a much larger object and it's much closer, so for example, a smaller moon getting close to Saturn, which is much, much larger than Earth, those tides become significant enough to actually stretch it and pull it apart completely. So that is what we think may have formed Saturn's rings. Now that's important then for moon formation because they will then start to form moons again from that debris disk or that ring. So a bit like when we had the giant impact with Earth and Theia, that smaller planet we expect hit us, we get this disk of material, and that starts to coalesce and clump together to form moons. Now, there's something interesting about Saturn's rings that's a little bit different, is that the edge of the ring is at a location known as the Roche limit. Now, what that means is that anything in or closer to Saturn, those tides from Saturn are too strong that it can't gravitationally come together to form a moon. But if anything went further away from Saturn, then actually the gravitational tides decrease and a moon can form. Now, you put all that together with the fact that that ring is actually spreading. So over time, again, happens on a relatively short time frame, but long time for us, it will spread outwards. And the edge of that ring then has less tide on it, less gravitational tides. So it can then start to clump together or coalesce. And that circle I've put there on the edge of Saturn's rings was a new moon that was forming on the ring edge. So whilst Cassini spacecraft was orbiting Saturn, it saw some fantastic things. And this is an example of what we saw. This was a moon or a clump of material forming right at the ring edge. So we got to see moons forming almost in real time from one of these rings. Now, when we kind of take a bit of a step back and look at Saturn and its structure of the moons, we can see that the further away they are, the larger they are. Now, when you think about the moons forming at the ring edge, it kind of makes sense. So when a moon forms, it takes away material from the ring. So the ring actually gets smaller because some of it then it grows into a moon. And each time a new moon forms, there's less ring there to form it. So each time a new moon forms, it gets smaller and smaller. And over time, these moons actually drift outwards. So we call it an orbital migration, but it basically means that these moons move further out and we get this sort of structure, which is actually quite interesting to have a look at. You can see the size distribution, it decreases as it gets closer to Saturn. And as time goes on, we expect smaller moons to actually form as we go on. Now, those ones are all quite interesting for me, but I think this one is the most interesting, and it concerns captured moons. So all of the moons that I showed you before are moons that are formed with the planet or they're formed around the planet. So they have some connection to the planet straight away. However, they can capture a moon or they can capture a planet, I should say. They can capture anything really. It then becomes a moon. So if we had a minor planet, an asteroid, or even another planet that was orbiting the sun, they're kind of going in the same direction. If it got too close to a larger planet, then the gravitational attraction from that planet is able to capture it, and it then basically becomes on a new orbit. So here you've got that kind of blue line here. You've got that minor planet orbiting the sun, and it comes close to Saturn, close enough that it can get gravitationally captured. It then places it onto a new orbit around Saturn, and it's then a moon. It wasn't a moon to start with, but because it got too close, it is now a captured moon. And this actually is, I say, relatively common in the sense that we found lots of them. We know that they're there, and we know there's lots of them. So, how do we know that? Well, these are the outer moons of Jupiter. If you look carefully in the center, you can see the Galilean moons, which is the purple circles. They are, or ellipses, they are the orbits of the Galilean moons, the ones that formed with Jupiter. You then got a blue group in the middle, which is the prograde group. Now, remember I mentioned that the Galilean moons go in the same direction that the planet rotates, or Jupiter rotates. Prograde satellites or moons are ones that go in the same direction that the planet rotates. So prograde, same direction as the Galilean moons. But the interesting group here is the retrograde one, which is the red. And these are located much further out, and they orbit in the opposite direction. Now, there's no way that they can end up on orbits like that if they formed with the planet. Because as I mentioned before, it takes an enormous amount of energy to actually place them on opposite orbits. Because if it's rotating in the same way as they form, then you conserve things like angular momentum. And you can't just flick that around. There's an enormous amount of energy involved there. So the only way they can really end up on those sorts of orbits is if they came from somewhere else to start with. And these groups are quite significant. There's large groups of these around Jupiter. I mean, it kind of makes sense, really, because Jupiter is a big planet. It has a large gravitational influence. Anything that gets too close, it can capture. So you've got this retrograde group. And it's probably worth noting that right in the middle of that, there's this green one. And recently it was found that there's a prograde one in the retrograde group. Now, that raises obviously questions to how it got there in the first place. It probably is a captured moon, but it's not going to survive very long. It's going the opposite way compared to the other ones, and it's very, very likely that there will be a head-on collision between some moons. And lots of these ring systems, even in Saturn's rings, it's expected that some of these collisions can almost replenish the ring systems. You've got two moons that collide, it then creates this debris around the planet again, and you get a new ring form. So there's almost like a mechanism that replenishes it over time. It's not a straightforward form a moon and it's done, because they can then recollide. So anyway, we have this group associated with Jupiter. Saturn also has the same thing. So again, you've got that prograde group closer to Saturn, which is blue. You then also got a retrograde group, which is further out, and then a green one, which is orbiting prograde in the retrograde group. So it's going opposite again. Now, the interesting thing here is that the objects that are going the opposite way, they're obviously captured objects. And they are very, very far away from the planet in the sense that there's a distance where they would be destabilized. But because they go in the opposite way, it might sound strange or doesn't really make much sense. But you can trust me that they are more stable. So the further away they are when they go in the opposite way, they're actually more stable than the ones that go in the same direction as the planet. Again, it's probably doesn't make a lot of sense, but they are more stable. So we have these groups, especially with Jupiter and Saturn, have been captured, and these are actually fairly small. They're probably like asteroid sort of size, so they're not that big necessarily. But it gets a little bit more exciting when we go a little bit further out. So we go to Neptune. Now, Neptune is right on the edge of our solar system. Okay, that's not technically true. It's the edge with regards to our planets, anyway. And it's close to the Kuiper Belt, which is where Pluto originates from, or where Pluto pretty much resides. And it has this large moon called Triton. Now, Triton is a captured moon. It's also larger than Pluto. It also has an atmosphere. So this is a fairly significant object that's been gravitationally captured by one of the gas giants. How do we know it's been captured? Well, again, it's orbiting the wrong way and it's very inclined. So that's another thing I didn't mention about Jupiter and Saturn. If I go back to Saturn, you can see it's quite inclined. And again, that's another indication that it's actually been captured, because if it wasn't inclined, it would form with it. So it's the same direction basically. But anyway, so Triton, this moon with an atmosphere that's bigger than Pluto, has been captured. And depending on where it was, could have potentially been a planet in its own right. It is basically a dwarf planet. And where it came from, the Kuiper Belt or further out, it's thought that it was originally a double or a binary dwarf planet. So what's happened here is you've got almost two Pluto-like objects orbiting themselves, and they've come too close to Neptune, One of them has actually been thrown away by that interaction, and one has been captured, which was Triton. So there could be another object out there which was Triton's twin, basically, that is now back out on its own. So it's a very interesting situation with Triton. And again, just to give you a bit of an idea, size-wise, of Pluto. So you've got Pluto on the left there, and Triton on the right. Now, Pluto does have a slight atmosphere as well as Triton, but it just puts it into context, really, that it's not necessarily the size that denotes it being a moon. It's its orbit, and you can capture these objects. And actually, if I want to kind of go a bit further and infer things with exoplanets, so exoplanets are planets that are orbiting other stars. We're looking for exomoons, which are moons orbiting those. We haven't really found um, any yet, but there's no reason why a lot of those really big gas giants we've found, which are not habitable, can't have a moon the size of Earth. So when we do models and simulations, we can show that these big gas giants we found, which are not habitable, they can have a Earth-size moon orbiting them, which actually raises some very interesting questions actually going forward, because we haven't really found that many habitable planets. But if we can find planets that can have an Earth-sized moon, what would life look like on that? Because we're on a planet, your seasons and things and your days are going to look very different on a moon compared to a planet. So it's interesting to kind of go forward. Now, these captured objects at the outer part of our solar system, they're expected to be, or thought to be centaurs. So these are objects that have orbits between the outer planets. So between Jupiter and Neptune, we've got a collection of these minor planets or asteroids, which are called centaurs. And because they're very close to the gas giants, they get scattered and bashed around a bit. So they have very unstable orbits, which means they can get very close to the planets, which then lead to being captured. So we expect that these are centaurs that have basically got, or their paths have crossed with the planets and they've been captured. But then where do these centaurs originate from? Because they're not stable and they don't live there permanently. It's kind of a bit of a temporary location for them. Well, we think that they originate from the scatter disk or the Kuiper Belt. So this is where Pluto originates from. It's further beyond Neptune, and we have a lot of smaller objects out there in this kind of disk-like structure. And interactions with planets themselves, they can actually get scattered inwards. So when you have a close encounter and not a collision, they can basically throw them inwards, a bit like a comet. The reason why we see comets is they get thrown inwards and then we see them. Same with the Kuiper Belt here, really. You're going to get them thrown inwards and then they might cross the path of a planet and get captured. And I'm going to come back to this a little bit later on because we can populate these with another population from somewhere else. So you've almost got a chain reaction, and looking at the very original location of these might actually offer some interesting questions, really, I suppose. So I'm going to diverge a little bit and look at interstellar objects. So we've looked at moons and how they get around the planets. And I want to just look at these and then come back to the moons at the very end. So in the last few years, I think 2017, 2016, we detected our first object that came from outside the solar system. So here we had an interstellar comet, an interstellar asteroid, and we saw it come through the solar system and then straight back out. And we got a couple of them here, and they just passed through. Now, why do we think they were interstellar? Were they? How do we know where they actually came from? Well, when we look at them, we can calculate how fast they're going. And they were traveling at incredible speeds. Speeds that means that they cannot be gravitationally bound to the sun. So the sun couldn't capture them. A bit like the planet can capture a moon, stars can capture planets, they can capture other asteroids that come too close. But these were traveling too fast. So they've actually gone in and back out again. And we captured them. Sorry, we didn't capture them. We actually imaged them, I should say, and we got some information from them. And you'll probably have heard about alien probes coming through, and specifically the one that went very close to the sun. It deviated away from its orbit in a way that didn't necessarily match anything natural. But there are a few processes that can knock it off its path. So, for example, if it's comet-like and it outgasses like a comet does, it can change its path. But it did change its path that we weren't entirely sure about. So that's why there's been some articles discussing whether it was an alien probe or something. And the interesting thing there is if we were to go and investigate our nearest star and send a spacecraft and a probe, the sort of trajectory we would take might look similar to one of these. We would blast it through the system and then try and image the planets along the way, and then it would be done. So we never got to see them in detail because they went in and out very fast. But the point is, we've had these two objects that have come through our solar system that didn't originate here. These have come from another star. They both too fast to be captured, and they didn't impact any planets. So they've just gone straight through. We didn't get to get a lot of information from them because they came in too fast. But anyway, they came in, didn't impact anything. But then this is where it gets interesting. So 2014, no, I said 2016, 17 is when those two came in. They were the first ones detected. But in 2014, one actually hit the Earth. This was a fairly small object, and it was only discovered very recently that this was interstellar, as in it came from outside the solar system, because they went back and they checked its speed, its velocity, and its trajectory, and it matched that of the other two. So actually, this was the first one to actually come into the system that we are aware of, and it actually hit Earth, and it caused a meteor. So as you're aware, as we have these smaller objects entering our upper atmosphere, they then burn up on entry and we get a meteor. So that was 2014. So it burnt up in the atmosphere, but some of the remains of that are expected to be at the bottom of the Pacific Ocean. So some of the remnants fell to the bottom of the ocean because we know where it hit on the planet, we know where it came from, and we know a good amount of information to approximate where this actually occurred. And this is approximately where it happened. So I think just north of Papua New Guinea, in the ocean there, and the Galileo Project is making or intending to look at recovering some of those fragments. Now, I don't know how plausible that is. You're trying to find out at the bottom of the ocean is going to be very difficult. But if we could, or if we could get any material that's coming from a different solar system or different star, it's going to tell us a lot of information about how planets form and other things as well. So if we can get this, this is going to be something that's formed with other planets, not our own. So it's going to be very, very interesting. And we've had 3 objects now coming from a different system. And this was about the size of the object they expected. So just under half a meter in diameter, and it was traveling about 60 kilometers per second. Now, just to put that into context, a long period comet from the Oort cloud, which is from the very, very edges of our solar system, it might have a velocity of about 50 kilometers per second, which is really fast. And then an object that hit the Earth from a near Earth orbit, like the asteroid belt, would be more on the order of 10 to 20 kilometers per second. So these interstellar objects are traveling very fast. And something that we probably going to have a look at in the future is they actually create a different sort of impact crater. If they're traveling much, much faster, the material behaves slightly different when it gets hit at very, very high velocity. So on the moon, which has obviously got a huge crater record, you can start to have a look at impact craters that look different to ones that hit us nearby. And you might be able to identify a location where an interstellar comet or asteroid hit the moon, and then we can go and explore that and learn a little bit more about it. But the thing I kind of want to leave with you really, and maybe to let you have a think about things, is could these interstellar objects have been captured from, well, by the solar system, by the sun, and then those themselves then get captured as moons? So have we already got objects in our solar system that came from another star system? So that Oort cloud, or not the Oort cloud, the Kuiper Belt and the scatter disk around the outer planets, where Pluto came from, and where Triton came from, it's possible that interstellar objects that come in can get captured there. And if those objects then get scattered inwards to be on orbits near the planets, they can get captured as a moon. So we know this from kind of models and stuff, that you can get captured and you can exchange material from one star to another. So I've got two stars here. We've got the Milky Way. Now the stars in the Milky Way are all traveling around the center. Think of it as cars on a road. They're all traveling kind of in a similar direction. It's got multiple lanes, and the stars are moving past each other, although they're going quite fast around the center of the Milky Way. Now, there can be material thrown out. So again, we had those giant collisions between planets early on. They don't have to collide, they can actually get close to each other instead. And instead of colliding, they can throw each other out. So then you have a planet thrown out from one star, then the next star picks it up. And we know from computer simulations that it's very possible to exchange material between different stars as they move around in a galaxy. So the thing to really think about here is, where did life actually originate from? It's probably one of our most fundamental questions, really, is how life started and why life is only really on Earth that we're aware of. But it could be that we came from somewhere else. There could be material coming in right now. Well, we know that there is. There's interstellar comets and asteroids coming in. They're hitting Earth. So exchanging material between the stars really kind of, it raises some very interesting questions, I suppose. So that was pretty much what I wanted to talk about, and I'm kind of losing my voice now anyway. But it's just a rough overview of how moons end up being moons. Now, that's not the full idea of it. There's a lot more going off and stuff like that, but it gives you a basic idea that they're not all formed together or in the same way. And if you're interested in anything to do with astrophysics, I have my own channel, which is called Astrophil, and I've got about 400 videos on there on various different things to do with moon, planets, stars, galaxies, and other interesting things. We also have our own channel for physics. So Physics in Lincoln, if you search for that, you'll find videos there which have got videos relating to other areas of physics. We have some astro chats there. So if you're interested in anything to do with astronomy, astrophysics, then go check out those videos. But what I'll do is I will leave it there. And if anyone has any questions that they want to ask, then pop them in the chat and I can try and answer them, really, I suppose. So I'll give you like about 5 minutes or so to pop a question in the chat if you want to, and I'll leave it there. So thank you for watching,